Welcome to Guide to Galaxy, this year's edition of Guide to Galaxy. Thank you all for coming. Let me start by introducing what is Guide to Galaxy. So this is a lecture series by the coordinators of Horizon, as you all know, the Physics and Astronomy Club of IIT Madras. This is the first session in Guide to Galaxy of this year, the physics of time. And let us start by asking why this topic in the first place. Why time? So, is time important? Should we be studying time? Why? Well, see, everything that happens is rooted inside time. There is nothing that happens which is not in an interval of time. But despite this fact, it does not get studied as rigorously as, let's say, forces, motion, or gravity. Somehow time gets pushed under the blanket. So this is one of the reasons why we chose this topic. We want you all to, if the session is successful, by the end of this, you'll have a different perspective of time, hopefully. So starting with that, yeah, this is a nice quote by Carlo Rovelli. The nature of time is perhaps the greatest remaining mystery. I think if there is a hall of the big questions which humanity has to solve, this would definitely find, the nature of time would definitely find a place in that hall. So, yeah, what is time? Don't expect to get the answer to this question from this session. We are not experts in this. But, let's see what Oxford has to say in this regard. It says, the indefinite continued progress of existence in events in the past, present, and future regarded as a whole. Let's see what Cambridge says. Yeah, something, 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 Britannica something. These are just words. Do they tell us exactly what time is? Do we understand it, the nature of time? Do we understand it inherently? And, okay, I hope all of us know what a thought experiment is. Einstein popularized the concept of a thought experiment. It's basically just you start with a hypothesis in your mind, at the back of your mind, and you think through its consequences, just by pure imagination. So, if we do a thought experiment, if we close our eyes and we try to imagine a universe without time, a reality without a concept of before or after, where nothing ever changes. You can actually try this sitting over here right now. It is a very good exercise. If we do this, then guess what will happen? We'll simply fail. When I did this personally, the first time I did this, I imagined a universe where everything was dead, everything was frozen where it was, planets were hanging around, atoms and molecules, all of this. But that is not a universe without time, is it? It is a universe without motion, not without time. I think we cannot imagine a universe without time. If someone can, it would be very great if they could share their idea. We have incentive also, chocolates. So, it is like imagining a color that does not exist, or a fifth or fourth dimension. So since we have nothing, we haven't seen it at all, it's very difficult to imagine, probably impossible. Oh yeah, so that idea of a universe which is dead, frozen, there is no motion in that universe, right? That was the closest I could get to an idea of a universe without time. Now, that leads us to a question. Would there be time if there was, I'm very sorry. Okay. Would there be time if there was no motion? Imagine this clock, imagine that clock stopping. Imagine all our clocks stopped suddenly. Would time still pass? Yes, it would. The fans would still move. Now imagine everything stops. There is no motion at all. Would time still pass? Yes, I see your nods. Now imagine your internal clocks also stop. There is no motion at all. Would there still be time? So this is one of the questions which sparked the debate between these two gentlemen. Newton was of the notion that it would still pass. Time is something absolute. It is a background, it is a backdrop in the course of which everything happens. Even if there was no one to observe, time would still pass, it would still exist. Whereas Leibniz was of a different notion. He said that no, if there is no one to observe, if there is no motion at all, then time would not exist because it is relational. It only exists because there is perception, because there is a measure. If there is no motion, then what would you measure time against? So, and the urban legend goes that in this debate, Leibniz removed that T, the second last letter of his surname, he removed it off in disagreement with Newton. And I remember seeing this during JEE. Sometimes they used to say Leibniz theorem, sometimes Leibniz theorem. Moving on, so there are many questions like these. Is time the fourth dimension? Is it an emergent quantity or a fundamental entity? Are we more tied to time than we are to space? Can it be stopped? Would time still exist if all motion were to cease to exist? Does time exist in us, or do we exist in it? There are many questions like these, and it is very worthy to think about these, to ponder about these. But today, as physicists over here, as physics enthusiasts over here, we will focus on the physics aspect of time, and we leave the philosophical aspects open to interpretation. We'll start with special relativity. We'll learn the basic concepts of special relativity. That would be around half of the session, and after that, we'll look at all of the domains of physics, what role time plays in all of them, and why we are focusing specially on special relativity, because this is the topic which flips our understanding of time upside down. So let's get started with special relativity.
Hi guys. So before going to special relativity, I feel like if we are learning about something which we don't know, we have to start from a point where we know. So let's start with good old relative motion. First of all, am I audible? Fine. Okay, so there's like two people approaching each other with the same velocity. So the velocity of one person with respect to the other is 2v, and it's trivial, right? So this is that VA B equal to VA minus VB, blah blah. Yeah, so that's relative motion, and we know this. But let's say a person is moving with a speed v, and he has a torch. He or she has a torch, and the light starts from the torch. He or she switched on the torch, and then light flows with the speed c. We know the speed of light is c, right? So we are stationary. That person is moving at a speed v with respect to us, and the light is moving with the speed c. So what is the speed of light with respect to us? C. Yeah, that's it. You all know special relativity. Nice. Let's start. Yeah, it's not v plus c, and that thing what you told is actually the second postulate of special relativity. Now this transformation is familiar. Let's say we have a frame A, and another frame B is moving with the speed v with respect to frame A. Yes, you had a doubt? Louder.
What motivates Einstein to take a second postulate in every frame?
I'll be coming. It's because of Maxwell. I'll be coming to it. So this is a familiar transformation to you. So there are two inertial frames. Inertial frames means the relative. A moves with respect to V with a constant velocity. There's no acceleration. If there is an acceleration, then the transformation equations that we are familiar with, x minus vt, right? X dash equal to x minus vt. That thing wouldn't be linear. It would be non-linear. It would have a t square term. So this we know as the Galilean transformation, where there's a point here xy, in this frame, the coordinates of this point is x and y. So this transformation, the Galilean transformation says or tells what the coordinates of that exact point with respect to that B frame. According to A frame, it's x and y, and according to B is actually x dash y dash, and these are the equations that relate those points. Now in this Galilean transformation, time is taken to be absolute, meaning in both A and B the time is the same. There is no change in time, like both of them perceive time as the same. But this transformation works well for Newtonian laws, but Maxwell came up with his famous 4 equations of electromagnetism, which is actually variant with this transformation. If we put Newtonian laws into this, the Newtonian laws are invariant under this transformation, but Maxwell's equations are not consistent with this. They are variant under this transformation. So Maxwell's theory suggests that the speed of light is constant for all observers. Maxwell's theory suggests that. That is because, see, the equations of Maxwell's and this wave equation, which if we do a an educated guess, or if we observe it, there's this term called 1 by mu naught epsilon naught in Maxwell's equation, and in wave equations there's this term called c square. So basically both are equivalent. So c square equal to 1 by mu naught epsilon naught, which means that in vacuum, for all observers, the speed of light should be the same. And from that, Einstein, with his imagination, obviously it takes a genius to actually spot out these facts, he used and then developed with the theory of relativity. And that's why the postulate 2 of special relativity is that speed of light is the same for all observers. And they came up with a transformation where Maxwell's equations are consistent. I mean, they are invariant under that transformation. And that transformation is what we call the Lorentz transformation. So, I mean, I'm just displaying the Lorentz transformation. We have to play around. We will play around, don't worry. It'll be fun. The thing is, I'll just display it for now. Just see. We can make observations. I mean, I would ask you about what do you observe from, I mean, what's the difference and what's the similarities between these two transformations. But yeah, under this transformation, Maxwell's theory as well as the Newtonian theory are invariant. And before we proceed, I've been telling postulate, second postulate is blah blah blah. We'll clearly see what are the postulates of SR, special relativity. First postulate, the laws of physics are the same in all inertial frames. Why did I put caps for physics? Is that all laws of physics are invariant under this transformation. I mean, all laws of physics are the same in all inertial frames in special relativity. But in Galilean transformation, only the Newtonian laws were invariant. And the second postulate is that the speed of light is the same for all observers in all frames of references. And yeah, we are going to use these two postulates alone, and we are going to make sense of the Lorentz transformation that I just blankly displayed to you all. So I guess we can dive into it. Before going into making sense of what Lorentz transformation is, what do you guys see similar in these two transformations? Y and Z same, okay. And?
B is equals to 0 the entire transformation.
What?
B is equals to 0 the transformation is the same.
No, if V is 0, X in Galilean X dash is X, but in Lorentz X dash is gamma X, no? Oh, okay. I mean, that means that we are in the same frame, no? We are not moving. We are in the same frame, correct? Only if it moves with a different velocity, then we can say that we are in a different frame, different inertial frame. So, what are the other similarities that you can find? I mean, there's another one which I am expecting.
X minus VT.
Yeah. X minus Vt, it is proportional. Right. It's just that in Lorentz, it's just scaled by a factor gamma. Right. And what are the differences? Yeah, there's a gamma. And that gamma is called as the Lorentz factor, which is the scaling factor. We'll be talking about that. And what is the other difference? Time is not constant. Instead, what is it? Is a function of? Velocity is constant. It's not a function. It's like something that varies. It's like time is now a function of both space and time. Before, time was just a function of time, and it was the same. It wasn't even. It's a function. It's a constant function. Now, time is a function of both space and time. That's the difference. Because in Galilean transformation, space coordinate was a function of space and time. So this also was an idea, like Farwell came up with. You guys know, right? So like that, if the space coordinate is a function of space and time, why not time could be a function of space and time? I mean, that's another idea that might ignited the idea to come up with Lorentz transformation. So yeah, the differences are that, okay, what exactly is the difference in the time t dash? There's some weird term, no, which I introduced just like that. Minus Vx by c square. So that V by c square thing and gamma, the differences between Galilean and Lorentz, right? We are exactly going to get those. Shall we? Okay, let's go. So to get gamma, I have to talk about light clocks. From now on, I think I will shift to the board. So first, what are clocks? Yes, exactly. Instruments to measure time. So how do they measure time?
They usually have watts.
What is that? What is that?
It oscillates and you measure it.
Time period. So basically we measure time with multiples of a small unit, which is the time period of some periodic motion. Yes, that's a clock. So in analog watches, the movement of the hand, the periodic motion, that if we take the time period and we measure time with multiples of those time periods. Now light clocks use light clocks use light to make a periodic motion, and then that time period is taken as a unit of time, and then it measures time. So let's see a very simple light clock consists of two mirrors which are exactly parallelly placed, and there's a distance, and let's say there's shoots up a photon and it goes at 90 degrees and it goes and strikes the other mirror and then comes back, goes up and comes down. This going from one mirror to the other and then coming back is one time period, and we measure time with the multiples of that time period. That's a light clock. Now let's say, we were having inertial frames, right? Let us put this into one inertial frame. So let's say this whole apparatus is moving with a constant velocity v with respect to us. We are stationary. Let us be stationary. With respect to us, that whole apparatus, that whole light clock is moving with the speed v. Another thing to mention, if you want to note down or something, don't feel shy or awkward. You can note down in case, because if I was there, I would have feel awkward. Just a note, light. So if it's moving, then let's say I'll just take 3 snapshots of the mirrors and I'll trace the path of the light fully. So now the light starts from here. Like we are stationary, the light clock is moving, so we will perceive the light to move like this and then come like this. I hope I did it. Yeah, symmetric, fine. Right. Fine. Laws of reflection, fine. So now this is how we will perceive if a light clock moves with the speed v. Oh, I should mention. We are going to use simple, very simple trigonometry to arrive at the value of gamma. I've been mentioning that the gamma's value is 1 by root of 1 minus v square by c square, right? It's the Lorentz factor. I'll be getting it using some simple trigonometry. Let's see. Now, what's the difference between these two? It's same as this, right? Now I have to define 4 quantities. ds. I want to do math here. Let me do it here. Yeah. ds, dm, ts, tm. Basically, ds is the distance traveled by the light when the clock is stationary, and dm is the distance traveled. I mean, in one way. Let's take for simplicity from here to here. Let that be ds. There's no harm. There'll be just like a factor of 2, which will get cancelled because it's just ratios. You'll be seeing it. It's just ratios. They'll get cancelled. So let this be, I mean, this is ds. No, then the clock is stationary. The distance traveled by the light is ds there, and then the time taken to travel is ts. Now here, this is dm, and this is ds, right? What about this distance? V, what t? Time in motion, right? Yes. Exactly. So now for the trigonometric part, I need an angle. So obviously, I'll take that as theta. Now, by the second postulate, we have to see the speed of light to be the same in all inertial frames of reference, right? I mean, no, actually all, but so the speed of light, okay, sorry. Yeah. So the speed of light is c, which is the distance traveled by the light in stationary divided by the time taken when the clock is stationary, which is equal to dm by tm. Okay. So what is sine theta? ds by dm. And from here I can get ts by tm equal to ts by tm. Okay. So which is equal to sine theta. I need this result. Now I'll take cos theta, because you see cos theta is v tm divided by dm. And what is dm? What is dm? C tm. Okay. V tm by c tm, which is just v by c, which is equal to cos theta. I've run out of space. Okay, fine. So using the identity, I mean, you all know. Sine theta equal to 1 minus cos square theta root. So what is sine theta? Ts by tm equal to root of 1 minus what is cos theta? V square by c square. And I need to find the time taken while the clock is moving as a function of time taken for the light to travel when it's stationary. So tm equal to ts divided by root of 1 minus v square by c square. And as we can see, the Lorentz factor, the scaling factor, has arrived here. So this is famously known as the time dilation. Now if you see, gamma value would always be greater than 1. I mean, greater than or equal. I mean, wait. not equal to, wait, it's always greater than 1 because v square, about that, speed of anything cannot exceed the speed of light. About that we will be talking why. I mean, you all know that nothing can travel faster than the speed of light, right? Using this postulate of SR and also another fact of invariant space-time interval, we can say that the limit of the speed of anything is the speed of light. So let's just take that for granted. We will talk about that, don't worry. So let's just take that for granted. So this quantity will always be lesser than 1. So this will be like lesser than 1 again. Square root of it will be lesser than 1. So inverse of this would be greater than 1. Fine. So we have gotten the scaling factor gamma. What else do we need to find? Yes?
Can you define what dm and ds are?
dm is the distance traveled by
dm and ds. Yeah.
time taken by the light to, reach from one mirror to other when it's stationary. Ts. Tm is time taken by the light to go from here to there while it's moving. Okay? So now that we have gotten the scaling factor gamma, what else do we need? What was the other thing? V by c square. Yes, the factor of v by c square, because t dash is a function of t and x, and like x is scaled by v by c square. Everything is scaled by gamma that we got. X alone is scaled by v by c square that we will talk about, but before going there,
When the mirrors are moving, then why should the light ray also change its direction? Why is it moving out of this direction? Why should it be the same?
when the whole apparatus is moving, we will actually see it like that. That appears like that. That will appear like that when the whole apparatus is moving and we are stationary.
That means like we are defining time with respect to time. We are like defining time like what we want, right? We are like
That is the meaning of definition, right? We're defining what we want to get.
then the time itself depends on.
That's the fact. Time depends. Time depends if we are moving. Time is not the same. That's the fact that we're trying to tell. That is time dilation. I mean, if it's fine if it's not clear, you can ask. You can drill me with questions at the end of the session. I'll be more than happy. So, but let the flow be. The flow is important actually to understand fully, because this is just simple. The next one needs a bit more of understanding of geometry and space-time diagrams, which I'll be guiding through, but still that needs more understanding. So let us go. You can drill me later. No issue. So this meme light, because see, if we are moving, time slows down for us. So if Panti is moving, so yeah. Let's come back. Yeah, we need the v by c square term, which you already told. For that, I guess we have to go to space-time diagrams. So, wait, I forgot. So you guys are familiar with velocity time, sorry, space time, distance time graph, right? Distance, time. Now for convenience, that the significance of why I'm changing time as the y-axis and distance as x-axis will be evident as we go through the space-time diagram, because if I tell it first, you won't understand. Even I didn't understand. So just bear with me. Let's say we have time here and then distance here. This, if I draw, let's say I'm at the origin at t equal to 0. At t equal to 0, I'm at x equal to 0. That's what it means when I say I'm at origin when t is 0. So if
Most of them.
I remain stationary.
I'm not sure about DD.
What would be my position at t equal to 1?
This guy is in physics. Some of them are in physics. Why? There are a mix of people.
Somewhere here? Goes no? So this is my trajectory in the space-time. So say,
Physics.
let's say if somebody is moving, let's say light itself.
23.
Let light, for the before moving to that, I have to scale the time axis with a factor of c. Why? Because
I'm in second year.
for convenience again. Let's say light, light travels at, light travels 3 into 10 power 8 meters
You must have seen
in 1
the
second, right?
orientation.
So at t equal to 1, it will be here.
200. Oh, you must.
Slope would be 1. And as I already told and taken for granted that the limit of speed is the speed of light, having a 45-degree angle would be convenient for us to check whether an object is within the limit or away from the limit. It will be easy for us. So that's why we are scaling by a factor of c.
So we'll be with you.
Now light's trajectory would be like, since it's scaled by ct,
I think yours.
and also both of them are now in units of length, so it will be convenient for us for
Setting
calculations.
with 22 batch DD.
Something like this, slope of 1. So this is the trajectory of a light ray starting from origin. So I've been talking about trajectories of me, light. Let's say some person is moving with speed v. Let that be half the speed of light. If they are moving at half the speed of light, then at t equal to 1, what would be their position? Which is 1.5 here. So it will be correct somewhere here. Correct? And if I start plotting at t equal to 2, it will be at 3, and it will be at 4.5 at t equal to 3. And if I draw that line, be somewhat like this. Forgive me for drawing skew lines, but I think you can get the idea. This is slope of 1, this is not, this is higher than slope of 1, as you can see. So this is why space-time diagrams are useful. We can, and the scaling also. So this is the trajectory of a person moving with the velocity v with respect to me. Everything is with respect to me because I am coinciding with the time axis. And the definition of being in the reference frame of one person is that my trajectory should be the time axis. That's the definition. Then this space-time diagram and all the trajectories are with respect to me. And I've been trailing trajectories, but those have a very cool name called the world line. So again, definition, if I want to see something from my frame of reference, then my world line should coincide with the t-axis, ct axis. And if again, why do we need transformations? Did you think we were talking about transformations, blah blah blah? Why do we need transformations? What are we going to do with that?
We want to describe whatever phenomena we are describing in respect of this frame here. So whoever is describing will be able to describe the same things.
Correct, but yeah, that's correct. But there's another important fact that needs to be told, is that no frame is special. So somebody might do all their calculations in one frame and somebody might do it in other. We know that all are correct. Like whatever they did is correct, whatever I did is correct. But
There should not be a mismatch.
there won't be. The thing is, if I want to see it from their perspective, let's say to simplify a problem. We go from one frame to another to simplify a problem. For that we need transformations. And see, if there is a special frame of reference, like this is like one frame of reference, and if we make that as special, then we don't need transformation. We just need one set of equations which map everything to that one frame of reference. But here we don't have one special frame of reference. That's why it's called reference, frame of reference. We don't have one. That's why transformations are important. Now let's say I want to see my motion in this person's frame of reference. Then what should I do?
apply a transformation so that you are now in the frame of reference.
I am apply a transformation.
To make yourself, to make your observations match up with it.
I should make a transformation such that the time axis coincides with their world line.
Just be scaled down.
Scale down is a different word. Not rotate, it's like shift. It's just shift.
Yeah.
Scaling down is like doing this. Get it? Huh?
You're not in velocity for that.
You're asking a question or making a statement? Fine. Okay. So, there's a video that explains everything very clearly. That lasts for 1 minute, don't worry. So yeah, as I told, if I want to see everything, the speed of, the motion of light as well as the motion of me from their frame of reference, I should make this as the time axis, and this is CT dash. So now here comes the second postulate of special relativity. What is that? So in their frame of reference also, the motion of light, the world line of light should be at a slope of 1 if we scaled it to CT. I'm going to ignore that from now on. I'm just going to say slope of 1. So this is why Lorentz transformation is important. It takes care of that very fact. That fact.
So if we just buy that CT dash, what is it?
CT dash is the we are doing a transformation such that we are viewing the world from this person's frame of reference.
So that is our view. That's your
Yes, and we do a Lorentz transformation. But I'm doing all this to get. I'm just making sense of the Lorentz transformation. I'm getting the value of v by c square from space-time diagrams. I've introduced space-time diagrams now. I will get to an example of people moving with speed v, shooting a target, and finding the slope of the x dash axis. That's how we'll get v by c square. But I know space-time is kind of like a very confusing topic, so let's see a video that makes it clear.
A mechanical device that does Lorentz transformations for you. Just like how a globe has the structure of rotations built into it in a fundamental way, and you can simply turn the globe to see how rotations work rather than doing a lot of complicated math, this space-time globe has Lorentz transformations built in. It does the math of special relativity for you, allowing you to focus on understanding the physics of motion from different perspectives. Here's a quick example. From my perspective, I'm always at the same position as time passes, while the cat is moving away from me to the right at 1/3 the speed of light, and the light rays from my light bulb are moving out to the right and left at the speed of light. Using the time globe, I can do a Lorentz transformation to boost into the cat naturally stays at the same position, x equals 0, as time passes, while the cat views me as moving away from it at 1/3 the speed of light to the left, and the speeds of the light rays from my light bulb are still the same, still at 45-degree angles.
Some sense made? Get an intuition? So they shifted from their frame of reference to the cat's frame of reference by doing Lorentz transformation, and the cat was like on the time axis now. So this is what Lorentz transformation like physically. So before moving on, Rohit is gonna talk about why speed of light is the limit.
Yeah, that line is continuous. In the video, it looks like there's discrete points, but it's continuous. So those points coming closer has nothing to do with the speed changing. Someone had a question. Yeah.
Just to clarify this, so the lines on the grid of the transparent sheet, that is the time that we observe the plane that we are in, or in the video.
Okay.
If you go back,
And it turns out that it's possible to.
yeah, so you have
And it turns out that it's possible.
lateral type sheet.
Yes.
So that is time that we see in our frame, in some ground frame that is not in the cat frame or the whatever person frame.
Space-time.
Like what are the axes? What are the so time is here and x-axis and -x are not on the box, right?
Wait, repeat your question.
This instance of time that we measure separately. It's all.
Can you please repeat the question again?
So
Sorry.
we have two grids on that we
Wait.
Mute it and play it.
I mean, no. Just give me a minute.
And it turns out that it's possible to actually build a mechanical device.
Where exactly do you have the doubt?
So the grid is the actual sheet.
It does Lorentz transformations for you. Just like
Okay,
how a globe
let me-
has the
let-
structure of rotation rather than doing all.
Let me explain it properly. So yeah, the x dash axis is not there here. The x dash axis is not there here. I'll tell you what happens here. I mean, it is there. I'll tell you where exactly it is.
Perpendicular to the box, not on the yes.
Yeah, it should be somewhere here. Like, the thing is, this space-time globe just helps you shift from one person's perspective to another, and to visualize why that is, like how that keeps the direction of light, the trajectory of light at the same 45 degrees. Yeah, it doesn't have the x axis. It has only the time axis. They have just mentioned that space like here. It's just that the parallel lines, the horizontal lines, positions. That's what they have told. There's no x-axis there. And yeah, just to shifting from one person's perspective to another, that understanding is very important, because I'm going to use this concept in the example that I'm going to do to get v by c square. It's not a derivation, by the way.
Another question.
Yes.
Related to this,
Okay.
if a person is moving
Okay.
and time is slower,
Yes.
so with respect to them, we are
Yes,
whose time is slower?
both of them. There's no correct one. It's all relative.
So according to us, like if the direction in which they are moving is important. If they're going farther from us, then let's say intuitively, if they are far away, time. There will be some time taken for the light from them to reach us. So the time, according to us, their time will slow down. But if they are approaching us, according to us, their time will speed up.
So it's okay for each of them that another.
Yeah, there is no correct, which like there's no like my time is correct. That's why that meme, like they're just accusing each other, but there's no absolute reference or something like that. It's just relative. But I'll tell everything according to me. According to me, if they're going far from me, away from me, time slows down. If they are coming towards me, time will speed up. Their time.
There's no way to check whose time is higher, because in order to check that, that's something. So it's velocity.
The thing is, there is no significance in doing that. That significance of whose time is faster breaks down. It's like RG breaks down.
Okay, so making postulates is fine. We establish the postulate that the speed of light is same in all frames of references.
What?
But
part you mentioned.
and Lorentz transformations came as something as a mathematical finding. So we found some functions which let the Maxwell's equations be invariant,
Simultaneity breaks that when
and that was a good
Okay,
discovery.
so-
But
so-
if something
okay, because
mathematically
it's
works,
v square
we also have to find a way to interpret it.
Yes,
And
yes, that's not
Poincare
difficult. I'll make
suggested
I'll make
that
point.
all laws of physics should
I
be
got anxiety.
should be the same in all inertial references.
I'll
So,
clarify it later. I'll clarify.
how
I got
to
anxiety because of the question.
how to let Newton's laws be invariant under Lorentz transformations?
fine.
Thank you so much for.
It's very simple.
Yeah.
You
How
say
did I
that
even
mass
not
is
think
no
about
longer
that?
a constant,
Delta T is
but we have relativistic mass.
Yeah.
And this
Yeah,
m is
the
just
gamma. I'll tell it. I'll tell it again.
so mass is
No, the
relativistic
thing
now.
is,
And
my physics prof, like not prof.
so I mean this
School teacher was telling
even
me
this has to
I
be
remember
interpreted.
it.
This has to be
That was
intuitively
all.
agreed upon.
Maybe switch back to
And
the slides.
that is why we should be
Showing
as
these slides,
as physics enthusiasts, a little skeptical sometimes. You should ask, why should we accept some postulate? Why can no object go over the speed of light? So is there some experimental evidence to this? That's what I asked, and I found the answer. It's one of the experiments, a very simple one, is this. It was made in 1962. It's available on YouTube in black and white videography. So it's called the ultimate speed by the Bertozzi experiment. I'll quickly describe what the experiment was about. So classically, in Newtonian physics, you're allowed to have infinite speed, right? So if I were to give, let's say g, 9.8 meter per second square acceleration to an object for 1 year. If I do it for 1 year, the speed of it would reach almost equal to the speed of light for 1 year. A few more months and then it should cross the speed of light, right? But does that happen? No. This was what was found out from this. So we have simple apparatus, an electron gun, a linear accelerator, one of the first particle accelerators, and oscilloscope, and what else? A calorimeter. Electrons are fired from one end of the gun. They are accelerated through the tube, and they hit the aluminum plate, which is the calorimeter. Now we measure the speed and the energy of these electrons. This is true in the classical limit, right? So the relation between kinetic energy and V square, which was expected, as you can guess, is a straight line. Something like, let's say this. But it was found that, and guess what is this? C or C square, yes, C square. Which means that no matter how much more energy you pump into those electrons, no matter how much more you accelerate them by increasing your fields, they would never cross the speed of light. This was a great discovery back in the 1900s, and yeah, so the mass of electrons really does slow down as the mass of electrons increases as they, because if this is what 1 by 1 upon, as V increases, what happens to this? Goes up, right? So mass, let's say you have, as you approach the speed of light, mass approaches infinity. You need infinite acceleration, infinite energy to keep going on beyond the speed of, so nothing which has mass can attain the speed of light. Only light can have the speed of light, because light has zero mass. 1 second. Yeah, go on.
Can you justify why you want to scale mass? Because I get why you want to scale position at time. Because
yes. Yeah, that's what I said. Poincare suggested that if you want to keep all the laws of physics invariant under Lorentz transformations. Now Maxwell's equations were correct. They were tested rigorously. This meant that Lorentz transformations had to be correct because they left Maxwell's equations invariant. So somehow you have to incorporate Lorentz into this, which left F is equals to ma invariant, the form of the equations here. That can be done very easily if you scale mass, if you consider mass as relativistic and not a constant. Are you satisfied?
I mean, see, like you have acceleration. Acceleration depends on position at time, and I cannot like straight up say that is not scale. I don't know. See whether.
Yeah, even I haven't. See, this is complicated. This comes under acceleration. Comes in general relativity. As in SR, we assume no acceleration, only inertial frames. So that is more complicated. GR comes into it. So even we haven't looked into it. But sure, that's a good question to ask. Yeah, this is the graph from the actual experiment that was done.
Actually, then let us not go into acceleration.
Yeah, we're not going into acceleration. This is all there is.
Keep it velocity.
Sure.
So like, take momentum.
Huh?
Take momentum.
Momentum.
Yeah. What is scale in momentum?
Mass is the same. Both the forms are still the same.
Right.
Okay.
does this mean that in different frames of reference, mass of an object will be?
Yes, relativistic mass. So we lost distance is no longer absolute, time is no longer absolute, mass is also no longer absolute. We will, after this, we'll derive the V by C square factors, we'll do it. So, yeah, we'll have a little bit more of SR.
Okay. So there's an example situation, and I have depicted that as a space-time diagram. Or before going back, before going forward, I want to clarify one thing that I told. I was telling that if I move farther away, if someone moves farther away, their time slows down, and if they're coming back, their time speeds up. No, not like that. The thing is that slowing down factor is the Lorentz factor, which is gamma, which is just 1 by root of 1 minus b square by c square. There's the magnitude of velocity, right? There's no sign, right? So anyways, time will slow down. If that's why I mentioned, if a body moves with respect to us, their time will slow down. It's just that the simultaneity will break down. The thing is, if they are moving farther away, then they'll be like, their event will be later for us. Like it will be, the relativity or simultaneity breaks down. I'll talk about that later. For now, the thing is, if some object moves with the velocity v with respect to us, then their time will slow down, and that is time dilation. Is it clear? Or are you guys sleeping? No? Okay, fine. Let's go to the example. So here there are two space shuttles, A and B. A is in pink, B is in blue. So both of them are like, the thing is, A and B are separated by a distance x naught, let's say, and there's some there's a target right at the center of both of them. Like they are moving the same speed v, that also I have to mention. They're moving the same speed v with respect to me. I'm stationary, so my world line coincides with that CT axis. Now this is the world line of A, world line of B. So their target is x naught. X naught will also move like that with respect to me, right? Because x naught the center point is with respect to them, correct? So that will also trace a path like that. Now the target is actually a laser light, and they will shoot it. They'll shoot it right after they start from their frame of references x-axis, that is the x-dash axis. They will shoot it. Makes sense, right? From their frame of reference, they will shoot it from their x-axis. So that is the x-dash axis with respect to us. Correct? So they are shooting and we are seeing it. For them, they started at the same time and the target hit at the same time. But for us, here only the relativity or simultaneity breaks down. For us, the starting point is not simultaneous, because if they started x naught with respect to us, it seems like the target is not hit. See, I have drawn it as a dotted line. These two are having slopes of 1, correct? Because it's light, it has to move with a slope. The world light should be with a slope of 1. So if I start from my frame of reference is x naught, then the slope is, the target is not simultaneous. Both of them are not hitting at the same place. Actually, same time. Same time. This is time axis, right? So they're not hitting at the same time. So they're starting at a different time, and then they're hitting same. Like the target is simultaneous for us, but not the starting point. So now what I'm trying to find is the delay in time, like the time lag between their start of shooting the laser, and I'm going to drop a perpendicular from this point, because this is the distance of B. This is the distance of B with respect to me from where the B starts the laser. Because they are moving, obviously their distance at which they start would be different for me. So that, seems to be different, as you can see. If they start from here, then the target is not reached. So if they shoot such that the target is reached, the the position of B is different. So So let me take that as xb. So the whole thing is xb, and this is delta t I'm taking. Delta t is basically, this is tb. I mean time taken by the shuttle B to reach that, I mean the time taken by the laser from B to reach the target is tb, and time taken by shuttle time taken by the laser from shuttle A to reach the target is ta. So the time lag I'm trying to find, and this thing. Why am I trying to find is that these two events must lie on their frames of references x axis. So these two lines must lie on the x dash axis. I'm trying to find the x dash axis from this space-time diagram. Okay? Because for them, these two events are simultaneous. So they ought to be lying in their x axis. So this is delta t. This is whole thing is xb. If I try to find the ratio, then that's basically the slope of x dash axis. Make sense? So even if it doesn't make sense, I'll go forward. After I finish everything, you can ask me doubts. So I'll write it somewhere here. Slope of x dash axis is equal to delta t by xb. Now what is delta t? I'll again drop a perpendicular. So this distance, so as I can see, if I want to find the slope of this, the slope of this is c, the yellow line. So c equal to x naught by 2 plus something divided by time taken by a. What is that? ta. So what is this thing? This is basically ta into v, because the relative velocity of a with respect to me is v and the time taken is ta, so vta. So if I solve this for ta, I will be getting x naught by 2 into c minus v. Similarly, if I do the math, okay, I'm running out of time. It's equal to x naught by 2 into, I mean slide is not necessary. Slide is not necessary. I'm just doing on the board plate. Because this has a negative slope, so this will become, here it will be minus c. So it will be like, this will be negative tbv. Now, now I need to find delta t, right? Delta t equal to ta minus tb, which is equal to x naught by 2 into c minus v minus x naught by 2 into c plus v, which is equal to x naught by 2 into c plus v minus c minus v by c square minus v square, which is equal to the c's will go off, so this will be there. So 2v, 2 goes cancel. So v x naught by c square minus v square is equal to delta t. This is what I'm getting. I've got delta t for the slope. Now I have to get xb. What is xb? xb is basically x naught plus again wait. So what is, yeah, so this time taken is delta t, and here this distance would be the relative velocity into delta t. So x naught plus v delta t. So I mean, do I have to do the math? Okay, I'll do it. Fine. So v into v square x naught by c square minus v square. I will get that this goes, so c square x naught by c square minus v square. Now, I mean delta t is important, xb is important. I'm going to rub this off. So slope, as I promised, slope x dash, slope of x dash axis equal to delta t by xb, which is equal to x naught by c square is common in them. So delta t by xb, v by c square. Okay. Now, what is this? Oh, by the way, I have taken this as CT dash, right? I am seeing, I'm trying to make a transformation into A's frame of reference. Sorry, I forgot to mention that. So that's why I've mentioned it as CT dash. And with respect to that, that being from, I'm making their A's origin and my A's frame of reference's origin and my origin as the same. So with respect to A, I'm finding the x dash axis. And B will be like just shifted from it, and it like the B's world line in that frame of reference would be just a parallel line with parallel to CT dash. B's world line in that frame. So this line's equation would be x equal to Vt, right? Or V by Ct. And what is this? Slope is V by C square. So y equal to mx. So these two are the lines. These two are the axes from my frame. These two are the equations of those axes with respect to my frame of reference. So now both of our origins are same, right? So their origin must map to our origin. So t dash must be 0 and x dash must be 0 with respect to A's frame of reference. So if these two are 0, then all the points lying on this will be in this t dash axis, right? And similarly, all the points in this must map to this. So I'll get t dash proportional to this would be mapped to 0, no? So t minus v by c square x, and x dash proportional to x minus vt. And we know the proportionality constant, we got it, and that's gamma, which is the Lorentz factor. And thus we have made sense of the Lorentz transformation. So this is a GIF that actually, with which we can visualize how the x dash and t dash axes transform. So the more they are tilted towards, the more the CT axis is tilted towards the speed of light, the more its velocity is. So accordingly, due to all these transformation equations, you will get that the slope of CT, here they have put just t, the slope of t dash is inverse of slope of x dash. That is trivial. If you manipulate the Lorentz transformation equations, you will get that slope of t dash is inverse of slope of x dash. That is trivial to get. I'm not going to do that now. And now that we have played with space-time diagrams, we will think of a situation where the world line of an object actually loops on itself. So those are, I'll leave the curiosity with Rohit. So.
One thing you could ask from this after this is that can the world line come back on itself? And this directly implies that at one point my future is my past, is meeting my past. So like this sounds all very fantastical, and it is, but a lot of math is involved, and we'll give you just one idea of how that may have come. As in the math, I mean, you'll see. Let's just start. So did we tell you okay, this is the space-time interval in Minkowski space-time. In Euclidean space-time, we all know that dx square plus dy square plus dz square defines the line element, length of the smallest line element. In Minkowski space-time, we have minus c square dt square plus dx square plus dy square plus dz square. I mean, these three positive and this one being negative can be altered. It's just that they have to be opposite in sign. That is inherent to the theory. Now, this is one of the metrics. Okay, in spherical polar, I hope you guys have learned spherical polar coordinates in 1010. You're doing it? Not yet. Okay, I mean, you will. This remains same, minus c square dt square plus dr square plus r square sine square theta d phi square, and what else? I missed out something. R square d theta, yeah, r square d theta square. We don't care about this anyway. All we care about is this and this. I'll tell you quickly what phi is, since you haven't done spherical polar coordinates. We have a sphere, and this is what we now use to describe points in space. Phi is my angle on the xy plane relative to the x-axis. Okay, fine. I'll rub and start.
Rub it. Or you explain. Yeah. You explain. Just
Phi is just the angle, and it goes from 0 to 2 pi. It can roll about the plane of the x-axis. Now, this is one of the metrics. In general relativity, there can be other functions over here in this place. What if there was a function of r over here and a function of r over here? Both of them were f of r, and f of r changed its sign after some value. No, I'm replacing this with f of r.
Okay, you're saying that? Okay.
Yeah, in some other metric, ds square is f of r dt square plus. Light cones. You want to talk about light cones?
Yeah, I just want to make them see. So.
Okay. And we should do it faster.
So, I'm randomly putting stuff and explaining. Sorry for, apologies if you find it a bit, awkward or something. But what's it?
It's not you to explain. What is the Minkowski space? What is the ds square?
So, okay, Minkowski is, take off the name for now, take away for the name. The thing ds square is actually called the space-time interval. This means now I told objects moving with speed, their time will slow down, but for that to, the speed of light should be constant. So there must be some change in length also, because speed is infinite, time is going up. So there must be some. I'm just telling it theoretically. We don't have time. We can do everything. So I'm just telling it. So if there is some change in time, there is also a change in length. There should be a change in length, so that speed of light is the same. So that is called length contraction that we do. We can now go to briefly time permits. So there, time dilation and length contraction both combine. Now, like for that, I have looked at Lorentz transformation. In the Lorentz transformation, we have seen that space coordinate is a function of space and time. Time coordinate is also a function of space and time. So space and time are basically intertwined. So they make a 3D space plus 1D time. That's why I prefer time as this axis. There will be 3D space and then this 1D time. So 4D space time, which is actually the so there's a 4D space time, and the distance between two events actually now from now they're not points on that space time 4D space time. They're not points. They're called events. So the distance between two events is given by this metric called ds square. So the most basic, there are different metrics. If any of you have attended our summer school, which happened like once ago in May, we were talking about metrics of black holes. So that was a part of GR, very intro GR, it was like that. So there we are talking about metrics, which basically gives us the geometry of the space-time. Space-time here in Minkowski means flat. It's just flat space-time. There's no curvature. And curvature comes in GR, which we don't have to treat physicists as such. So yeah, ds square is actually a space-time interval. And the simplest of all is flat space-time, which is Minkowski. And that we, transformed it into spherical polar and explained about CTCs where this 5 coordinate becomes time and then it goes from 0 to 2 pi. So there's kind of like the starting point and ending point are same. That's why the world length is kind of curved. So before actually making sense of this light cone thing, you will see some codes hanging around, right? So I'll talk about light cones very fast. As explained before with the Bernoulli's experiment, I claimed that speed of light should be the limit, right? Because that's a consequence of this invariant time. Okay, coming back to space-time intervals, there should be some quantity that should be constant, and that is this space-time interval. Before, the length was constant, right? In Euclidean space, whatever transformation you do, the length or the norm would be the same. Like that here, now both time and space are changing, so there should be something that remains constant. So that is space-time interval, and that's another reason why the time coordinate has one sign and the space coordinates have one sign, different signs. They are not same because there is some compensation between them. I'm telling all this like just theory because time constraints. Here can do everything with time. Do everything. So why did I put this? Invariant space-time interval. Since speed of light is constant and this ds square, whatever transformation you do, ds square would be the same in all terms. Ds square, the space-time interval. That's why speed of light is the limit. That's why we get. That's the consequence, and we showed from Madras experiment that C is the limit. Closed time-like curves. Sorry. CTCs are not cost. Not what you think is closed time-like curves. So let's have since I told you like this is a space-time diagram, and I'm taking this as an event. This point apparently a point, but actually an event. So now let me draw the 45 degrees because we know the speed of light is the limit, right? Now we have to talk very quickly about this concept of causality, which means that if two events are said to be causal, then one could be the cause of the other. That is causality. For that to happen, they should be separated into space-time such that they will take some velocity lesser than the speed of light to reach the limit. Make sense? So for causality, two events must be somewhere in this region and in this region. So, okay, fine. So events in these two sides are causally connected, totally causally connected, because if there is an event here and event here, within the speed, with the speed lesser than the speed of light, I can reach from one event to other, and I can effectively cause this event to happen. This event can cause that event to happen. So this gives rise to kind of like a region where everything is allowed. And what about this region? No. The thing is, if there are two events here, so if there are two events here, from going from here to here, I have to have a slope which is lesser than 1. Correct. So information cannot pass from this event to that event. They are independent. They are not causally connected. Even then, what is the what? And these means it's in the light cone of this event. I'm talking about from like. Okay, I have to make that point also clear. If there are these 2 points you're saying, right? Then I have to construct these. It's in the causal region of it. So this is a region that these two regions are. Yes. So now these two regions are called to be like time-like separated, because their separation in space and time, if we see the separation in time dominates more than the separation in space. That's why they are called time-like. And then if they are according to this event, and if they are here, then they are called space-like. They are in the space-like
on green, right?
Part of the space-time diagram. Which means that the spatial separation dominates over the time-like separation. So that's why. The thing is, another thing, I told you, to compensate for ds square to be like the same, one should be negative, one should be positive. It can be either way also. The space can be negative and the time can be positive. So in that way, it can also be. It's just a convention that I took time as negative and space as positive. Okay, so if the space is negative and time is positive, then here if people are familiar with this SR, I mean seniors, if they are familiar, this sometimes according to that, I guess this is v square minus c square. So this would be negative, right? I'll tell you about seniors. Are you getting this? Would be ds square greater than 0. This would be ds square greater than 0. But if that convention is flipped, then this would be positive and the outside would be negative. So I don't like to call this region with respect to ds square sign time-like, space-like. Either way, if it is positive or negative or whatever convention we are choosing, it will be time-like only. This one will be time-like. This would be space-like. Yes. Yes, exactly. Now here it's trivial to get the space-time coordinates as ds square equal to minus c square dt square plus v square dt square, where v square dt square is basically dr by dt the whole square into dt square. Dt square is basically dt the whole square, so I have cancelled, which is dr square, which is dx square plus dy square plus dx square, which is the spatial separation. So another form of writing the Minkowski is this one, and we are going to use this to say why, what is this line according with ds square. If I put v as c, that means light. Correct. So if I put v as c, I am getting ds square as 0. So these two lines correspond to ds square equal to 0. Again, how did I arrive it as 45 degrees? I can, because c square dt square equal to, let's say here I have taken only x. So in this diagram it is just dx square. So in natural units, this is just, I mean, oh, I've scaled this as, okay, did I scale it? No, I did not scale it. So it's just dt square equal to ds square. Scaling is for our convenience. I scaled it here because for the example, it would be convenient if I scale it to ct. So here if I do, then that's why it's 45 and my negative 45. So if this is in 1D, if I do it in 2D, it will be a cone. If it's in 3D, it's a 4D cone. Make sense? And these are light cones. And then now, it's like if I draw like a let me do it the 4 quadrants. There's some world line of an object. Let's say like this, something like this. Why? So the light cones would actually travel like this. Because for this event, any problem? So if for this event, the light cones would be like this. There it is 45 degrees at that point. Again here, again here, again here. So we told CTC has a world line which is looping on itself. So now it does make sense, right? This is the world line. And if we see, these two events are actually causally connected. Because if I extend this event is lying in the, yes. According to the event, no? Oh, that you're telling. Okay, yeah. Please. The thing is, I'm moving my axis with it. My axis changes with my world line. It's like there's this axis. It just goes like this. That's why the cones look like that. Because my axis moves. Because if I'm at an event, I should draw axis like, like this, tangent to the world line, and then construct 45 degrees and correct cone.
They're still in SR, and then shouldn't the series still be 45 degrees, irrespective of the frame? Now if you move to the nothing frame, your axis is going to just get like this. So C is still going to be the bisector of the T and X.
We're not in SR anymore.
Huh?
We're in GR, so that's why.
Yeah, the thing is, you want to talk about that?
Saying we're not in SR.
As you told, like you'd asked whether it's in SR, right?
Yeah.
Actually, CTCs
Yeah, you cannot
come in GR.
So if you're drawing this in SR, then it has to be.
Yeah, it has to be just like
Yeah, the same like.
CTC to explain that thing. I combined SR with GR, but yeah, it's good that you pointed it out. It's not SR actually; it's kind of GR. The thing is, the CTCs are actually we could get solutions of the Einstein field equation which explains GR, and CTCs are mathematically possible solutions to Einstein field equation. So we wanted to talk about the closed time-like curves because it has time and it tells like one event could be your past and can also be your future. So that's a possible trajectory is what I'm trying to tell.
What is the thing that limits us from moving in GR? Like, what do you have to do to get that? Is there some like accelerating value that you have to go to?
I mean, there are solutions of Einstein field equation which I'm not that much familiar with. I mean, yeah. So if we if we go into GR, then we can talk about more about CTCs. But why I wanted to show this to you is that I want to introduce light cones, which I did, and then closed time-like curves, which, like, you know, as I told, present present can also be the future. It's like kind of loop. Events can happen again, so which is not making intuitive sense, but it does exist mathematically for now, theoretically, but not. We haven't seen much. That's what. So.
Survey we have covered today. It is the most basic form of SR. You can do a course in the physics department on special relativity. It's very, I mean, special relativity is just as confusing as quantum mechanics. It's not easy. Moving on, zooming out from SR, we come to time in physics. Again, let us start from the very basics. What is physics? What do we do in physics? If you think about it, in physics, it's all about the science of change. From Newton's laws to Maxwell's equations to Schrodinger's equation to cosmology, thermodynamics, all talk about how things evolve in time, according to time. So, physics is the science of change. In fact, science itself, all domains of science are about change, how things evolve in time. But the interesting thing is that all domains of physics, they have a different consequence on time. Time is interpreted different in many domains of physics. It is worthwhile to visit all of these and see what are the differences and appreciate them. So we'll start with classical mechanics, but even before that, let us start with ourselves. What is time to us in our daily lives as laymen? For most practical purposes, time is something very natural, right? There is nothing very confusing about it. It is something that flows from the past to the future, and all things happen in time. A universal now exists. Both of us can agree upon something happening at a simultaneous instant. And reality, okay, that I talked about. Everything passes through time. So it is something fundamental. And yeah, that's all there is to it. Unless, of course, there isn't. As we go into classical mechanics, what do we do in classical mechanics? We talk of objects' position, velocity, force, time, Newton's laws of motions, energy, momentum, trajectories of particles, how they evolve in time. While doing all of this, during all of this discourse, time is assumed to have some implicit attributes. Those are very natural. You can guess. You can also guess. Is time universal? Yes. Is time absolute in classical mechanics? It is. Is time real? Yes, obviously it is. What I think time is real. At least in classical mechanics. It's not in quantum gravity, but we'll come to that. Now, what else? What else? Time is linear. Can you agree to that?
Yes.
The amount of time passing right now is the same as in 1 second. Is the same amount will pass in another second? Huh?
1 second remains the same.
Yeah, 1 second remains the same. So, absolute and universal, linear, real, scalar. Okay, I'll talk about reversal symmetry. Let me just display all of these. Yeah. It is independent. It does not depend on other things. Other things depend on time, but time does not depend on other things. Agreed? It is continuous. You can cut down a second into how much ever you want. You can go to infinity. It is continuous. It's not discrete. Reversal symmetry. Now, what this means is that if you were to reverse the direction sign of time, if you were to send t to minus t, the basic laws of physics would still remain the same. F is equals to m would still hold. Other laws would still hold, just in reverse. It would still be allowed. Let's say there was a projectile motion. It would just go this way. That's all that would happen. And physics does not object the ball going back. So, these are the attributes in classical mechanics. As we go into relativistic physics, now there is no longer space. There is space-time. Agreed? So, the fourth dimension is time. This has deeper consequences than like, I mean, now a simple stone lying on the desk is not a thing. What is it? It's an event. Okay, chocolates to both of you. Come after the session. So it's an event. We all are events. There are no things. Relativistic mechanics tells us how events happen. It tells us how events happen in local frames and how local times evolve with respect to each other. Relativistic physics tells Einstein's equations tell us how to relate two frames of references, and things happen. Events happen in my reference. Time can stretch and contract now, so it is no longer linear. We saw in Lorentz transformations, it is a function of space and time. It wasn't linear anymore. Linearity is lost. It can contract, so a second is no longer a second for another. It can dilate. In relativity, time is no longer absolute and no longer independent. Now, can you guess why is it not independent? What does it depend upon? Louder? Space and space, yes. Time actually on speed. Time depends on velocity. What else? I'm talking about relativistic physics, not special relativistic physics. What else does it? Mass, yes, mass or gravity. In general relativity, the closer you are to mass, the slower time passes for you, because mass creates a valley in the fabric of space-time. You might have seen some animations or photos. So this does not happen in some other universe. It happens right now in here. For my legs, time passes slow. For all of us, time passes slower for our minds. This means that if a person was living on a mountain top, he would have more time in his life than relative to someone living at sea level. And this has been actually tested in experiment called as the Haffel-Keating experiment. Richard Haffel and I forgot the first name of Keating, they took atomic clocks on aeroplanes and went around the world. When they returned, there was a obvious difference in them. And those results agreed with the predictions of relativistic physics. So this means that you and I can no longer agree on when an event is happening, when exactly the event is happening, because we no longer have a common concept of present, past or future. If we just saw light cones, right? It could very well be that one event is in your future, but it's in my past. Relative to me, it's in past. For you, it's in future. This very well happens at very high speeds and very large separations. So this means that there is no longer a universal present or past or future. Everything is relative. So which of us are correct? Is my frame correct? Is yours correct? None of them. All of them. All of them are correct. There is no true frame. There is no one special frame. All of them are correct. So there are as many frames as there are points in space. All of these form a multitude of space-time. All of these form a multitude of times. A legion of times. And physics tells us how to relate these times, as I talked about, how local times evolve with respect to each other. A stone is a classic example of a thing. We can ask where it will be tomorrow, in the primitive sense. Conversely, a kiss is an event. It makes no sense to ask where the kiss will be tomorrow. The world is made up of networks of kisses, not of stones. Coming to quantum mechanics. Shruti will quickly talk about this.
So, coming to quantum mechanics. In quantum mechanics, there are operators and observables that are like the integral part of QM. Time has no operator, and time is not an observable. So, unlike position and momentum, time doesn't have an operator, so it's not a measurable, an observable quantity. So that's how, it's just a parameter again, which is like in the backdrop. It's there, and we do everything with respect to time, So since time doesn't have an operator, is it like a quantity that's derived from a more fundamental quantity? This is another way to look at it. I mean, there are no experimental evidences for all that. It's just that we switch from math to just philosophical talk. I mean, not philosophical. It's just that this is like a different view of time in quantum mechanics. Is time in quantum mechanics derived from a more fundamental property or fundamental quantity? Turns out it might be. There are quantum states and the oscillation of, say, an electron from one state to another. I'm saying it very vaguely. Even I don't know what it is. The thing is, I have a vague idea. I'll just tell it to you. So that the transitions of electrons from one quantum state to another. So from that time, like this time period for that transition. So that is a fundamental quantity. The transition is a fundamental quantity from which time is derived. So it's like that, but it's okay to leave it like, time doesn't have an operator, doesn't have an observable, so we don't know what it is exactly. So it's like that. And we have this smallest unit of time called the Planck time. So this is gotten from the three constants called the Planck constant, speed of light, and g. I mean, if you have had the PSS's shirt, HCG, yeah, those three constitute Planck time, Planck length, and Planck mass, and Planck energy. Let's go. So yeah, Planck time is gotten from that. So beyond this Planck time, if we go to time scales lesser than the Planck time, the thing is, due to the Heisenberg's uncertainty principle lying around, quantum effects on time will take on itself and makes time fuzzy. Again, like position and momentum, time also becomes fuzzy. So this is another way to interpret time in quantum mechanics. So there is no conclusive. This Planck time might indicate some quantization of time. I'm not telling there's no conclusive evidence, but there are suggestions like might be possible. But yeah, what if time is quantized? That's another way to talk about. But there's no evidence, or there's no like theoretical. It's just a philosophy and stuff. What is it out?
No, you're talking about quantizing time. So when does this Planck time concept come? Does it come from like standard QM or QM when you apply relativity?
Yeah, it's not standard QM. It's it's a subset of QM, very very small subset of QM where time might be quantized. So it's just
occurs when what restrictions do you place on what postulates do you place on QM?
If we go to I'm not sure about that. I don't want to comment about that. But yeah, there's another idea like that, but I don't want to talk more about that. It's like, since I talked about Planck time, I just wanted to tell, if we go, time is fuzzy. Now I would like to call upon Rohit to talk about
Why? Because none of the other domains of physics, neither classical mechanics nor quantum mechanics nor cosmology or what are the other domains? Relativistic physics. None of the other domains of physics impose a direction on time. Thermodynamics does that. Can you guess how? Second law, entropy. Exactly. Entropy is... Thermodynamics introduces the arrow of time, the irreversible flow from order to disorder. The second law states that entropy never decreases. It only increases, and that imposes a direction on time. Entropy is simply because the concept of entropy arises because simply there are many more ordered states than there are disordered. It's just more probable. Yeah, Eddington described the arrow of time. By the way, this arrow of time, entire thing was introduced by Eddington. So he said that if you draw an arrow arbitrarily, And as you move along the arrow, if you find more disorder in the universe, random element in the universe, then you're going towards the future. If you find more order, more non-random element, then you're moving in the past. This is the only law that distinguishes the past from the future. Otherwise, in classical mechanics, if you play a video of a ball bouncing, you can never say whether the video is playing in reverse or in forwards. But if the ball was rolling on the ground and it comes to a stop, if you play it in reverse, there's certainly something wrong. The ball cannot start by itself. Heat is being lost, and whenever energy spreads, there is an increase of entropy. Yeah. This is the paper of Clausius where he introduces entropy. He says that I want to name entropies something like energy because the both are very similar in their physical meanings. So, I mean, this is in German, but this is I thought there's an apple pie over here. So, Carl Sagan, I hope you all know Carl Sagan. Yes? Carl Sagan once said that if you want to make an apple pie, does anyone know? If you want to make an apple pie, you first have to invent the universe, is what Carl Sagan said. Sean Carroll said that no, if you want to make an apple pie, there is another way. You just have to sit and wait and watch and wait for the atoms of the universe to go into that specific arrangement so that you get an apple pie. And that's true. It's all a play of probability. You start with a random clump of atoms, and if you shine light on it for long enough, it should not be so surprising that you get a plant. What this is trying to say is that life itself might have evolved to accelerate the increase of entropy, because life is a very, very good way to increase entropy. For every one photon coming from the sun, we send out 8 more photons into space. The sun is not a source of energy. If you have watched Veritasium's video, you would be knowing this. The sun is not a source of energy for us. We radiate back almost all of the energy. The sun is a source of low entropy for us. After thermodynamics, we go into cosmology. Now, cosmology does also give another arrow of time. How? The expansion of the universe. The reason I said thermodynamics is the only one, because this arrow is very much linked to thermodynamics itself. Cosmology and thermodynamics are linked in the sense that expansion of the universe causes an increase in entropy. The expansion happens in one direction, right? This also gives a natural arrow of time. Let's say there were some galaxies scattered around, and I take a photo of it. After some time, I take many photos of it scattered over a long time. Now I can arrange these photographs in a chronological order. How? They have moved. I know that as time passes, the galaxies have moved apart, because in cosmology, you guys do know that the universe is expanding, right? Yeah. Good. Awesome. So, the very fact that I can arrange those photographs in a chronological order gives a concept of past, present, future. That is the arrow of time. Yeah. Now, when you combine cosmology and quantum mechanics, I was actually supposed to hide that thing, but okay, fine. So you get imaginary time in some of the theories. How? Why? Math. To simplify some problems, we use iota t instead of t. That's all. And once we are done simplifying the problem, we extract the real part out of out of complex time. So this is, see, for now this is a mathematical tool, for now. But it might turn out that complex time is more fundamental and real time is just what we experience of it. It very well might turn out so. So, yeah. Coming to high energy physics.
I can understand. I'll go very fast. Don't worry. So in high energy physics, it is the physics. It is also called as particle physics. So where we study about particle collisions, and in there how time is seen. It's again a crucial parameter. It's just in the backdrop with which we model all motion. So now there time plays a very important role in this very important theorem in high energy physics called the CPT theorem. CPT theorem states that, I'll tell what CPT are. C is charge, P is parity, T is time. So I'll tell it in very simple words. It's simple only, but still I'll tell it in a fun way. So I have C, P, T, 3 buttons, and this is in my universe. Now let me toggle C. If I toggle C, matter will change to antimatter. Let me toggle P also. Parity means having left-handed and right-handed axes. They are different, but they are symmetric. So I'm toggling parity also, like left-handed to right-handed or right-handed to left, whatever. I'm just toggling it. And then time. If it's forward, backward. If it's backward, forward. So time reversal also. If I do all these 3 at the same time, I will arrive at a universe which is equivalent to what I started with. If I toggle everything, all 3 at the same time. Because if I toggle one thing, then those 2 universes are not, I wouldn't say universe, that's like I don't want to use the word universe, like a situation or a condition, a system. We'll tell it as a system. So if I change just C, if I toggle just C, then those systems won't be symmetric. Only if I change, even if I change 2 pairwise, no, still they will be asymmetric, and there are proofs for that, and people have got Nobel prizes for that. You can go and check it out. So I'll just tell one. The parity, not parity. I forgot what they disproved. Before they thought if I toggle only parity or only charge or only time, it will be symmetric. So somebody got a Nobel Prize for the first time. It was a woman. She refused to go to vacation, and she found the asymmetry in, I think it's parity, I'm not sure. It was a woman who refused to go to some vacation with their family. So
Was that about 60?
huh?
Was that about 60?
Yes, exactly. Yeah, even I forgot. I looked it up, but I forgot. But yeah, so, and another 2 people got disproving these got, but all 3, if I toggle, they'll be the same. That's only CPT. But the thing is again, we talked about arrow of time. So in very rare cases, I don't want to talk about what the conditions of those rare cases are. So in rare cases, even if I change all 3, there is some asymmetry. That is because of the arrow of time. Arrow of time is like set due to thermodynamics and entropy. We talked about that. So it's in one direction. So in rare cases, there is also asymmetry in CPT theorem. CPT theorem is very important. They use it everywhere in HEP. So that theorem is also kind of inconsistent. So it's a very big thing. And yeah, time is the culprit there. So this is how time is viewed in HEP.
So yeah, we started out with this, didn't we? And is there any one property which we did not destroy? No, scalar was okay. Yeah, scalar is the only one we. Yeah. We're approaching the end of the session. Just 5 more minutes and done. This is on, right? Except scalar, all of these turned out to be untrue. Special relativity broke down, destroyed independent, quantum destroyed continuous, quantum gravity destroyed real, reversal symmetry, high energy physics, and absolute and universe was also special relativity also. So congratulations on completing the journey of destroying time as we know. Which brings us to
Yeah. I mean, there's a meme after that, so. Is that a slide? Then 2 slides. So, the theory of everything. I mean, this is very, like people who mostly the people present here would be knowing about this book. So there's this chapter called the theory of everything in that.
The last chapter.
Yes, the last chapter. So last chapter of our session and also the last chapter of this book. I'm just going to read some lines which actually tells about the book. Okay, first of all, I wanted to talk about the theory of everything because we are telling time is interpreted as like this in this domain, this like this in domain, right? What is actually time? There should be some universal, what to say, perception of time, right? I mean, about that also I talk about it. He has written in the book, Why? He has written in the book, but yeah, he has told that there should be a theory of everything. So there should be a universal notion of time. So that would be obtained only after we have gotten to the theory of everything. That's why I'm going to talk very, very quickly about this. So, wait a minute. At the moment, we have a number of partial theories. We have general relativity, the partial theory of gravity, and partial theories that govern the weak, strong, and the electromagnetic forces. So the last 3, the last 3 are like they can be combined into the so-called the grand unification. You can see there in green, right? This is taken from one Coursera course by University of Tokyo. You can see there. So this I didn't put it in the resource and reference, so don't scam me. So these are, the main difficulty in finding a theory that unifies gravity with the other forces is that general relativity is a classical theory. That is, it does not incorporate the uncertainty principle of quantum mechanics. So the necessary first step to approach the theory of everything is to combine GR with uncertainty principle. That's the starting point. And then he talks about string theory, which I don't want to talk about. You can read it up. And he's like, it's likely that answers to these questions, the questions that he asked, you go and read, will be found over the next few years, and that by the end of the century we shall know whether string theory is indeed the long sought after unifying theory of physics. So can there really be here only the question of whether theory of everything is like, do we need one theory of everything, or are we just okay with all these partial theories? The thing is, there seem to be 3 possibilities for this. There really is a complete unified theory which we will someday discover if we are smart enough. And there is no ultimate theory of the universe. There's just an infinite sequence of theories that describe the universe more and more accurately. And the third possibility is that there is no theory of everything. There's no theory of universe. The third one, even I can tell like it's absurd, because we have theories and it works, and we have come till this point where my voice is being recorded there, and there's all tech going in there, and we belong to Institute of Technology. That, if theories are not there, we wouldn't come here. So there are a lot of advancements, so theory must be there. So that leads us to the first 2, and the second one is like there's some limit. Again, there's a limit. He has also mentioned that, however, it seems that gravity may provide a limit to this sequence of box within boxes, the second possibility of having infinitely many theories. If one had a particle with energy above what is called the Planck energy, again Planck stuff, which is 10 to the power 19 giga eV, with its mass would be so concentrated that it would cut itself from the rest of the universe and form a little black hole. So there is also a limit for going in, infinite theories. So it comes back to the first possibility that there is a theory of everything. And yeah, this is the last time I'm going to quote. So what would it mean if we actually did discover the ultimate theory of the universe? it would mean that we shall be able to take part in this discussion of why the universe itself exists. If we try to find that, and if we find answer to that, it would be the ultimate triumph of human reason. And I would like to quote Stephen Hawking. He wrote it in Brief History of Time, not in this. Our goal is nothing less than our goal is nothing less than a complete description of the universe we live in. So yeah, that's why. So the time that we perceive in the theory of everything is the time, and we don't know about it, and we will know when TOE comes. Thank you for being such a great, cute audience.
This is much more better. You can read this.
Because we didn't spend time in writing this. So yeah.
We say that Einstein was a patent clerk, but what was he doing as a patent clerk? Synchronization of clocks. And more importantly, these are resources and references which we used and which also have further content. So separately, special relativity, time and physics, you can actually go through them. The first book on that side that formed the major content of this session. The Order of Time by Carlo Rovelli.
Guys, please wait for a while. We'll take a photo.
Yeah. Oh, one second. For chocolates, you won't get randomly. You have to tell. You will, but you have to tell. Okay, tell me the reference of Newton in this picture. Principia. That was easy. Quantum mechanics. You don't get to. Okay, tell what else? What are the light cone? Yes, ice cream cone, light cone. Black hole. What domain? General relativity, general and quantum gravity. Schrodinger's cat. Okay. What else? What is that guy over there? This? Yes. Not time crystal. Yes, but more specifically, solid state physics. Which one? The flower is just biology. Huh?